Okay, I posted some problems, practice problems for writing the mechanisms of free radical halogenation, as well as predicting the major products on the February 15th, which was Friday's folder. They have narrated answer keys to go with them. And I have a take-home quiz for Wednesday that you can get or that I'll give you for writing the initiation, propagation, termination steps for free radical halogenation. Okay, so where we want to start with, I guess it's kind of the end of the free radical chapter 15, and then moves us into, free radical chapter 18 moves us into 19, is this idea that when we brominate with either light, well, it's going to be light at room temperature. When I do a selective bromination, before we get to double bonds, the bromine is always going to go to the tertiary position, then a secondary position, and it's the major product's not going to be the primary position unless it's at high temperatures. So the same thing is true for this allylic position. If you're going to brominate a double bond with free radical halogenation, it's going to put the bromine in the allylic position. That's the most selective of the positions. And if you're going to if you're going to brominate an alkyl benzene, then it's going to go into the benzylic position as the most selective position, so that you'll always put the bromine in that benzylic position. And the reason for that is because the extra stability of the radical at those positions, because of the resonance structures. Okay. So the last and the only thing we have left to deal with radicals is this first reaction that I wrote doesn't work. This is not the major product of the reaction. What is? How many bromines? So what if I wrote that reaction and I left out the light and the heat? What would be the product of that reaction? I'd add, right. I'm going to add 2 bromines to a double bond trans. So whether there's light or heat present, the bromine is going to basically do addition to the double bond. So adding light or heat doesn't help me in terms of doing free radical halogenation, because the double bond portion is going to be much more reactive to bromine. So that means that if we add bromine, I can't control with the double bond whether it adds or whether it does free radical halogenation. It's going to do addition. Now, this reaction with the benzene, that reaction is okay because bromine will not add to a benzene ring by itself. Because the benzene ring is too stable, that we'll see end of this week, beginning of next week. So that means that I need another reagent to do free radical halogenation with double bonds. And that other reagent is this one, which is called NBS, N-bromosuccinimide. Okay. So NBS is a source of bromine atoms. It does not produce bromine molecule. And so it basically is used, we have to use a little bit of heat with the NBS to get it to break apart into its Br dot. And then that will do free radical halogenation. So again, if you try and do this reaction with bromine and light, that's not going to work. Instead, you're going to have to use NBS in order to get free radical halogenation. So that was what was wrong with the reaction from the other day. Now you can use NBS with alkanes, but it would be the equivalent of light at room temperature, because you really can't do NBS at high temperatures. So that should be the end of chapter whatever, 18. And if you already finished up your problems, then you know that already. And it said for Canvas that they were due by 7 minutes ago. But remember, there's no deadline, so if you get them done today, that's fine. Maybe tomorrow I'll record the scores. After that, you're kind of on your own every day. The percentage of, or the probability of me writing the scores down goes higher. So after this, you're gambling. Okay, so that's the end of the free radical halogenation. All right, any questions? So now let's move on to allylic carbocations. Bless you. Now, allylic carbocations are going to be kind of interesting from the standpoint of their stability. So a primary carbocation would normally not be stable. An allylic primary carbocation is. So we could write its resonance structure like this. And then the resonance hybrid would be averaging the bonds and averaging the charges. So in this case, the left is this is a double bond and a single bond, average, partial double. Single bond, double bond, partial double bond. And then as far as the charges go, for a lot of these molecules, wherever there's a plus charge, there's going to be a delta plus in a resonance hybrid. So we have the two delta positive charges at the end. So we have to be able to write the resonance structure as well as the hybrid. Now let's make things a little bit more interesting here. And let's see, how do I want to do this? I'll do a slightly different reaction than I did this morning. So let's take that alcohol and let's add HBr to it. first step in the mechanism. Protonate the oxygen. Okay, what happens next? Water leaves. What kind of mechanism am I doing? SN1. Now, because I have a carbocation that has resonance structures, possible, I'm going to need to do some extra steps here. So I'm going to go to the next page, and I'm going to say, okay, here is my carbocation. Does it have a resonance structure? Yes, can we draw it? Can I draw the hybrid? And there's the hybrid. So, which carbon, A or B, is the bromine going to add to? Hold on. Do we all have an answer in our head as to which one the bromine is going to add to? Yes, we do. Then I can just randomly call on somebody. B. Okay, got one vote for B.
Zach Litwinowicz.
I got two B's. Any A's? One A? It's either yes or no. Two A's. Three A's. Okay, so let's write the two products then. Here's the BR as it's when the BR comes in and adds to carbon B, we get product B, and if the BR minus comes in and adds to that carbon, we get product A. Now you might say, well, wait, you just reacted the resonance structures as if they were the intermediates. Yes. And I did that to avoid the confusion of adding the bromine to one of these two delta positive charges and figure out where the double bond goes after that. So what we're going to do is we're going to treat the resin structures as if they were each individual intermediates. So that gives me product B and product A. So let me re-ask. Well, let me not re-ask the question. Let me ask a different question for this. And here's my question. What is the major product of this reaction going to be? Is it going to be B? Or is it going to be A? You have a minute to discuss.
Do you think A or B? So this one's going to be the most stable product. This is the first.
Okay, your time is up. Let me ask again. Let me ask around.
Casey Lindstrom.
What do you think? B? Okay, we got one vote for B.
Emily James.
I'm going to go
Emily James.
We already got yours. We got yours. Oh, you should have said another one.
Anthony Deddick.
You already. B. Okay, how many people say B? How many say A? Okay. So we've got more B's than A's. Why are people choosing B?
Because the bromine adds the secondary load carbocation rather than the
Okay, and what's special about the secondary? It's more stable. So product B is coming from the more stable intermediate. Why are people choosing A?
Because the intermediate with the alkene component has more, it's more substituted.
Okay, this double bond is more substituted. Did you look at it from the standpoint of this intermediate or of the product? You indicated you looked at it up here with the intermediate, but that's also true for the product, right? So what we have is product B. Well, okay, first we need to establish some ground rules. The ground rules are, when I'm looking at the intermediates, carbocation stability is first, and then double bond stability. When I'm looking at the product, double bond stability. Right? Because I've never established rules about which bromide is more stable, primary, secondary, or tertiary. We don't have that rule. But we do have rules about double bonds more substituted being more stable. So I'm going to look at I'm going to look at B or A here. I'm going to look at product A from the standpoint that it's the more stable product. So where does the major product come from? The more stable intermediate or the more stable product? going to depend on the energy. It's also going to depend on the reaction time. So the answer to this question is, which one is the major product? It depends. Because I have two things that are fighting against each other here. The stability of the intermediate and the stability of the product. So in order to fully explain this, let's draw a reaction coordinate diagram for this reaction. And I'm going to have to start in the middle with the resonance hybrid. And here's what we're going to have to translate secondary and primary radicals stability into. The fact that when the bromine reacts with the secondary carbocation, it's going to have a lower activation energy than when it reacts with the primary carbocation. So in other words, when a bromine adds to the primary position, it's going to have a higher activation energy than when it reacts with at the secondary position in this resonance hybrid. Okay. So this molecule, when it's sitting here in the middle, and it's going to add a Br minus to it, it can go left or it can go right. So, my next question is, which way is it going to go the faster of the two? Is it going to go to the right or is it going to go to the left? Let's all answer on 3. I heard right. Maybe a left here and there. It's going to go right. It's going to go faster here. Why? It's got lower activation energy. Okay, so it's going to go, the reaction is going to go faster to the right at room temperature. Now what if I raise the temperature? Which way is it going to go faster? Give you a second to think about that. If I raise the temperature, and I'm not going to raise it to some ridiculously high temperature like 300 degrees, like the free radical halogenation. I'm just going to, no, I'll double the temperature. Which way is the reaction going to go faster? To the right or to the left? Okay. Ready?
Right.
Good. It's still going to go faster to the right, even if I give it more energy. So my question is, how am I ever going to get the major product to be the product on the left? Let's fill that in. Let's fill in the diagram. So over here I'm going to have my there's that product, which was product A, right? And then over here I'm going to have no, sorry, never mind. Let's write it the correct way. Product B on the left or on the right. Product A on the left. How do I ever get product A? Because I said it depends. Well, how's it going to depend if I'm always forming product B faster and all I do is raise the temperature?
If you extend how long the reaction goes on, then more energy.
All right, so I'm in short reaction time. I don't know, 10 seconds. What product am I going to have more of? B. Right, that's the one that's formed fastest. All right, so now I make it 10 days. Which product formed fastest? Still B. So how did I get A? What? Does it come back?
So does D such low activation energy does react back?
Backwards. You're getting close.
Reverse.
Reverse. So imagine I'm starting this reaction and the fastest product that forms is B. What happens if B loses its bromide? It's going to go back to the middle. Can that happen? Yes. How much energy is it going to take? Well, lots of relative term. How about this much? And I wanted that in red. Apparently, I'm not allowed to have it in red. How about this here? Oh, you're killing me. Okay. Raw. Yeah, oh, well, I can't. This is going to be monochrome. Okay, so here's my reverse reaction. That's the activation energy of the reverse reaction to go from the product back over the activation barrier to the middle. Now, we said product B was less stable than product A, so I've included that in my diagram. So I might as well at this point put in that there would be an activation energy in reverse for going from product A back to the middle. So what we're not taking into account that we need to right now is the reversibility of this reaction. So I start my reaction out and I form product B the fastest. If I raise the temperature of the reaction and I give it more time to react, what's going to happen? Some of that B is going to reverse itself and go back to the middle. And then where is most of it going to go from there? Most of it's going to go where? Back to B. But maybe, let's say, 2 molecules out of 100 go to A. What happens when they go to A? They're going to stay there. They're going to kind of get stuck there because the activation barrier that they have to overcome to get back to the middle now is so much bigger than for B. So if I raise the temperature and I allow the reaction to go on, for a long time, whatever long time is. Then if it's 2 molecules out of every 100, eventually those get siphoned off into product A and they can't return. So at some point in time, I'm going to have more A than B. Now I'm always going to have a little bit of B, and I'm always going to have a little bit of A. But whereas if I use low temperature, low energy, short reaction times, I'm going to favor this. So I'm going to favor that product when I have a short reaction time or a relatively low temperature. I'm going to favor product B. On the other hand, if I use a higher temp and a long reaction time, the system's going to have time to reverse itself, go and form product A, and get stuck in that well and not come out of it. So under those conditions, A is going to be my major product. And again, I'm talking about major and minor, majority products, not exclusively 100%. So what's new here is the reversibility of the reaction. And so any potential group that I put in that allylic position that is a potential leaving group, this can happen with. Everybody can see that? So I can choose my major or minor product by choosing the reaction conditions. Now let's give these names. The product that comes from the most stable intermediate is going to be called the kinetic product. It comes from the most stable intermediate. Technically, the kinetic product is the first formed. Why? Or fastest formed? Because it comes from the more stable intermediate. What's the most stable product? What? I'm going to call that the thermodynamic product. So I'm going to end up with a thermodynamic product and a kinetic product. Thermodynamic product is going to be favored at higher temperature, long reaction times. The kinetic product is going to be short reaction times, low temperatures. That's when they're going to be favored. So I could convert this reaction to either one of these two products by adjusting the reaction conditions. And this diagram is the reason why. All right. Everybody with me? So, let's extend this. This was basically substituting something at the allylic position. What I'd like to do is to move to what are called conjugated diamines. A conjugated diene means you've got a double bond, single bond, double bond. They alternate. Those are more stable than what we would call an isolated diene. An isolated dienes are easy. Each double bond will react independent of the other, and I can do all the reactions of double bonds on my isolated diene. So that just took chapter 13, no, chapter 12, and now brought it into play. Particularly if I gave you a homework assignment and said, hey, write the products, I could give you an isolated diene and ask you all the double bond reactions from last semester. Everything. But let's talk about conjugated systems. Because conjugated systems are a little more interesting. So let's say that I've got my 1,3-butadiene molecule. And I always like to take these systems and I like to number the conjugated system from number 1 to 4. Whether that's the IUPAC numbering system or not, I always like to call them 1, 2, 3, and 4. So I'm going to go to a new page and just do that. So there's 1, there's 2, there's 3, and there's 4. Now I'm going to add HBr to this. So where should I add the H+? Well, what would Markovnikov's rule say? Better yet, what would a broad interpretation of Markovnikov's rule say? Add the hydrogen to form the most stable intermediate. Right? That's the broad view of Markovnikov's rule. Add the hydrogen to make the most stable intermediate. So am I going to add the H+ to 2? No. Am I going to add the H+ to 3? No. I'm always going to add the H+ to either carbon 1 or carbon 4. Always. So I always add at the ends. So the rules for this, the rules for adding the conjugated dienes are add the H+ or add the electrophile to the end of the 4-carbon system, carbon 1 or carbon 4. Now I'll show you why that still is okay with Markovnikov's rule. So let's add the H+ to carbon 1. Oh, I need to take an aside here. Notice how I wrote from the double bond to the H+, the way the arrow is going. But if you didn't catch that, I'll do it again. Remember, the arrow always moves from electron rich towards the positive charge. And I wouldn't be saying that if I didn't have to write that on a whole bunch of your take-home quiz problems. So hopefully by exam 3, I won't have to write that arrow. I won't have to correct your arrow going in the wrong direction. All right, done with the aside. Let's add the H to carbon 1. What did I just make? A secondary allylic carbocation. What does it have? Another resonance structure. It's kind of like deja vu. What? Normally I would say that means you've seen it before, but you just saw it like 10 minutes ago. Which carbocation is more stable? One on the left, one on the right. Left. So the left one, when my Br minus comes in and adds, what am I going to form? The more, no. And then when I add the Br minus to the second carbocation, what am I going to form? So, in terms of this reaction, this is what we're going to call 1,2 and 1,4 addition. But other than adding the H plus to the conjugated diene and then forming the carbocation, the allylic carbocation, the rest of this we just did. Okay, so which one of these two is the kinetic product? Left? Left is the kinetic product. Thermodynamic product. Does it always have to be that way? No, not necessarily. If there's only one product, then they're both the kinetic and the thermodynamic product, which really doesn't mean much. If there's only one product, it means there's only one product. No matter how I change the conditions, I only get one product. So that's the difference here. So I've got a kinetic and I've got a thermodynamic product. In the kinetic product case, I added a 1, a 2, a 3, and a 4. I added the HBr to carbons 1 and 2 respectively. In the thermodynamic product, I added my two groups to the 1 and the 4 position with the double bond moving now between 2 and 3. So if I just would have started with this without talking about allylic carbocations and their resonance structures, you would have predicted the 1,2 product. When the 1,4 product showed up, you would have gone, where did that come from? But now we know because it's the allylic carbocation. Basically, we've drawn both resonance structures and we treat those as the same. Right. So doing the 1,2 and the 1,4 addition is what it's called, is very similar to what we started with. The idea of making the allylic carbocation. And the diagram that's in these notes, which are the notes for the lecture or the video from today, this is essentially the diagram you would see in it, is exactly what we did before. The idea that when the double bond is in the middle, that product's more stable. When the double bond's at the end, that product's less stable. But to form the less stable product, you go through a lower activation energy, and to form the more stable product, you go through the higher activation energy. So in this case, we can make either product by changing the reaction conditions. All right, is everybody okay with that? Now, the question that I would have is the 1,2 product always kinetic? Is the 1,4 product always thermodynamic? No. You got to take it on a case-by-case basis. So if I change the structure a little bit, I can get the 1,2 to be thermodynamic and the 1,4 to be kinetic. It just depends on the structure. What? No, well, I'll give you a couple of examples of that on Wednesday. I reserve the right to make them take-home problems. Well, how else are you going to learn? Right? So that's the difference. Now I could say, did anybody have a sense of deja vu from chapter 3 from last semester on this? When we taught, okay, the answer is no, you didn't have a sense of deja vu if you're asking me. The only person that probably did was me. But if you go back and you take a look at it, we talked about activation energy, stability of the products. There's some beautiful diagrams where they're parallel to each other, and then there's some diagrams where they crisscross. Nice attempt by Top Hat to introduce this topic of thermodynamic and kinetic in the first semester. You know, I guess in Canada, students must remember things better going through, the entire semester. But that's why we're going back and we're reviewing it now. Okay, so this is going to be a generalized topic. The more stable intermediate will always give you the kinetic product. The more stable product will always be thermodynamic. And there will be some other examples of this that we'll do. Okay? And like I said, I'll probably give you some more problems, one take home to do on Wednesday about this, these types of 1, 2, 1, 4, and just show you that you got to take them individually. All right. So I think that's it for today. Now I do have your graded problems from the other day, and you can grab your homework problems